So we say, okay, probability and chi-squared value. We either compare the p-value to the significance level or the chi-squared value to the critical value. We've been given the critical value, and it says, what should we conclude? So we're going to compare the critical value with our chi-squared value. So, oops. 3.83 in comparison to 5.991. Our chi-squared value is less than our critical value. And if p is low, we reject the h sub o, which means that we fail to reject if it's low for chi-squared. So since our chi-squared value is lower than the critical value, we fail to reject the null hypothesis, which means essentially we accept the null hypothesis. So since we accept the null hypothesis, this means that the sample essentially does follow the same distribution as Lorenzo's year, which is p-value. Our p-value, the probability is pretty high. It's higher than 10%, right? So our significance level is 5%. So it's definitely going to be larger than 5%. It's saying, hey, the probability is pretty large that our observed would fall out this way if we expected it to fall out this way, right? So if we observed our distribution to be this when we expected it to be this, what's the probability that it did become this? And this is saying, 14.8%, not very high, but what they're saying in regards to the significance level, 1%, 5%, 10%, we only start rejecting stuff when it's that low, when it's less than 10%. And since it's higher than 10%, that statistically speaking, that means it's a pretty high statistic for that to happen, or a pretty high probability for that to happen. So that's essentially what all of this means. I don't know if I did the best job explaining it, but thankfully we'll have 2 more times to try, and you will understand it hopefully by the end of these notes. Okay, so another goodness of fit test. How do I know that? Because this whole lesson is goodness of fit. And it says the time taken by an 8-year-old child to solve a puzzle can be modeled by a normal distribution with a mean of 12 and a standard deviation of 2.5. Times taken to solve the same puzzle by a random sample of 50 10-year-old children are as follows. So the numbers that are given to us are always going to be the observed frequency, right? So that's our observed frequency. It says test using a 10% significance level whether the times of the 10-year-old children come from the same distribution. The idea that it comes from the same distribution, that we're talking about following a certain distribution, that's how I know that it's goodness of fit, right? If it's asking about some type of, hey, is it following this type of distribution? That's how you know it's a goodness of fit. Okay. So I'm going to go through and make sure I've listed out all the same steps because it hasn't asked me like part A, part B, part C. It's not walking me through the test, which sometimes in IB, they will only give you a problem that looks like this. No parts A, B, or C. They might just say, hey, run the test. So you need to know all the things that are included with running the test. This now follows the general procedure from 9.1. General procedure, the very first thing that you did, you need to make sure that you hit all 6 of those points. Okay, so if you want to follow along, I'm going to number those procedure steps. The first step from that procedure from 9.1 was that we need to formulate hypotheses. Very important. Make sure that you always start out with your hypotheses. Our null hypothesis for a goodness of fit test is always that it does follow the distribution that we expect it to follow. In this case, the distribution that we expect it to follow is a normal distribution with an average of that and a standard deviation of that. So I'm going to say the sample follows the distribution n comma 12, n parentheses 12 comma 2.5 squared. Remember that this is how we talk about normal distributions, average comma variance, and variance is just your standard deviation squared. And so if you want to be specific about the type of distribution, which you should always be specific with your hypotheses, this would be a way that you could write it out. Or you could also just say follows the normal distribution with an average of 12 and a standard deviation of 2.5. But you do need to make sure that you list those out in the hypotheses, or else you're not being specific enough. So just be very careful. The alternative, of course, is that it doesn't. So the sample does not, et cetera, et cetera. Which means that our alternative could mean that the average is actually 13 or that the standard deviation is actually 3, right? So that's why we have to make sure that we're very specific with these hypotheses, is that it could just be that it still follows a normal distribution, just our averages and standard deviations are wrong. So just keep that in mind. That's why we need to be specific. So that's part 1 of the procedure. Part 2 of the procedure is that we need to choose our significance level, which it's always given to us. It's 10%. Which is 0.10. Step 3 is then to use data from our sample to calculate the test statistic. And in that step, we need to make sure that we also calculate expected if we haven't already been given expected value. So this is how we need to go through now and think about, okay, well, how do we expect it to go? In example 1, we expected it to follow a certain percentage or probability breakdown, right? We said, okay, a third, a fourth, and 5/12. So we had to go through and calculate what is a third, a fourth, and 5/12 in order to get our expected values. So we observed 10, 11, 25, and then 4. That's what we observed in terms of the distributions. What we expected it to follow was a normal distribution. So what we have to do is we have to figure out what is the probability of being less than 9. So if I were to go run that and figure out what is the probability of being less than 9, I would go run my normal distributions, probability, 5, normal CDF. My lower bound is negative infinity. My upper bound is 9. My average is 12. My standard deviation is 2.5. So the probability of being less than 9 is 0.11506, etc. If I'm doing that out of 60 students, out of 50 children, I would then multiply this by 50, which means I expect for there to be 5.75. So what I did is I took the probability of X being less than or equal to 9, and then I multiplied it by 50, the total number of students in the sample. There were 50 of them, and so I took the probability and then multiplied it by 50. So out of the 50, 5.75 should be in this category. Let me show you again. In order to find the expected value for this guy, I know that that's between 9 and 11. So I first calculate the probability of being between 9 and 11, the probability, right? Lower bound 9, upper bound 11, average 12, standard deviation 2.5. The probability of being between 9 and 11 is that. So then in order to turn that into expected, I multiply it by the total number of people in the sample. So that's multiply by 50. So I expect there to be 11.48. I'll do 2 decimal places for all of these. So to find the next expected, I need to find the probability of being in this column. probability of being between 11 and 13, average 12, standard deviation 2.5. And then I take that probability and I multiply it by 50, the total number of people in the sample. So that means I expect there to be 15.54. And remember, expected values are okay to be decimals because it's like an average. Again, running probability of being between 13 and 15. And then multiply that by 50 to find out how many I expect. And then lower bound 15, upper bound infinity, 12, 2.5, multiply by 50, 5.75. Notice that they're symmetric. And why is that? It's because our normal distributions follow a symmetric curve, right? And so this is just us seeing the normal distribution in a symmetric way. Okay, so that's how we found all of the expected, right? So you follow the distribution to find the expected. And remember that how you find expected is the probability of that thing multiplied by the total number in the sample. Now we have all of the information we need in order to plug this into our calculator.